This final recording on lecture 6 concerns species concentration. So we're looking again at the internal flow, but in that case, instead of considering thermal or hydrodynamic condition, we aim to describe how concentration of species in a mixture can convect and change as you go along the axis of the pipe. The problem is very similar to the thermal problem. In fact, I see there, I forgot to change that term here. That should be concentration entrance region. So what do we describe is a pipe, which is of constant cross section. Fluid comes into the pipe with uniform condition, velocity, and species concentration. We're dealing with a mixture of two species A and B, and just focus on how the mass concentration of species A evolves over space. So species concentration of species A is written rho A. R is variable or function of radial position, and x equals 0. So at that point, we can assume things to be constant. So instead of having a dependence on R, well, there is a dependence on R, but we say that it is constant. Once the fluid enters the pipe and is exposed to a condition at the wall of the pipe which is different from what's outside, that is, you can have either a uniform wall concentration or a uniform wall flux of species, flux of species A. And these two conditions will change the way concentration is distributed inside the pipe. You end up creating a concentration boundary layer, which will emerge at the end of the concentration entrance region. And after that, you're in the fully developed region. So everything there, it's the same diagram as the thermal problem. I've copied it essentially, but changed the variable from temperature to concentration rho A. Depending on the condition, you may observe different trends. So for example, if it's a uniform wall concentration, you see that the concentration, that is the position of the red curve at the wall, is always going to be the same. The distance from the axis to that red curve will be the same. But because you keep on allowing species A to enter the pipe domain, your mean concentration over the cross-section will increase. The minimum value, which is at that point, will also increase. And that's for the case where rho A at the surface is greater than rho A in the fluid. So you end up diffusing and transporting that mass of species A into the pipe from the boundary. So that curve, which is initially perhaps quite curved like that, will gradually flatten more and more. And if the pipe is extremely long, you'll end up with just a vertical line. If you've got a uniform wall flux of species A, then what you end up is with this curve here, and the distance from the cross-section to the curve at the wall will increase gradually, as well as the mean, as well as the minimum as well. They all increase, and the longer the pipe, the higher the species concentration can be, but up to a limit imposed perhaps by what is physically possible in terms of concentration. Concentration can't go over 100% concentration. So what are the various terms we need to define? First, the thickness of the concentration boundary layer, delta C, is related to the thickness of the hydrodynamic boundary layer by this ratio where we use the Schmidt number to the power n, a power n. So we know that the Schmidt number determines the relative strength of the two concentration, or thickness of the two concentration boundary, the two boundary layers. In the same way as the thickness of the hydrodynamic boundary layer was related to the thickness of the thermal boundary layer by the Prandtl number. Definitions for the mass, if it's a problem like this one, it means that you may have perhaps a gas here and a liquid film on the wall, then it's a problem of evaporation, but it could be another kind of phase change. So we have a transfer of species A to the fluid. You could have a solid that becomes a gas or a liquid or anything like that. So evaporation is just an example. You can add a species as you go from the inlet to the outlet. And if you want to measure the rate of addition of species A, you look at what comes out of the whole domain compared to what went in. And to calculate the actual mass of species A's that goes through the section, for example, this one here, you multiply the concentration of the mass concentration of species A by the velocity of the fluid by the area. So this is the volumetric flow rate, U times dAc. And if you multiply by the mass concentration, you get a transfer of mass of species A through that cross section. So when we look at the balance from the inlet to the outlet, we know the total amount that's been added to the fluid as it flows through our pipe section. The equivalent to this is given as the second equation, where we use the definition of the mean of the concentration and the concentration of the mass. Okay, so M here stands for the mean written like this: mass concentration species A at the outlet, and you take the mean. So that means you don't have to use that area integral. Definition of the mean is provided here, and for a cylindrical pipe, the area integral ends up being this, with this coefficient there. The laminar boundary layer would have an entrance length, which is determined by the Reynolds number and the Schmidt number, instead of the Prandtl number for the thermal boundary layer. For the turbulent case, we use the usual value of 10 for the relative distance to the diameter. And for the fully developed region, we know we have this relationship that holds true throughout the fully developed region. So essentially, it's the exact same as for the thermal problem, but we substituted the mass concentration for the temperature. All the correlations for the mass transfer coefficient Hm are obtained from the thermal correlation by replacing Prandtl number by the Schmidt number. So it's quite simple. We don't need to introduce new correlations. They are in the formula sheet, and you can use these, but you replace Prandtl by Schmidt. It means also, because of the similarity, we can apply the exact same derivation in order to prove certain things, such as, for example, the relationship between the evolution of the mass concentration through the system. For a uniform wall concentration boundary condition, you end up with the exact same formula as the one we had for the uniform wall temperature. It means we also have a log mean concentration difference that drives mass transfer in this problem. The method is the exact same. So it means the graphs are the same, I reuse the same, but I change the variable to concentration instead of temperature. And that's the end.